The ultimate goal in this lecture is to construct the fermionic part of the BFSS action on the lattice. But before doing that, we need to address two fundamental issues, the fermion doubling problem and its resolution through the Wilson term. So in this first part, we focus entirely on these two ideas, explaining them carefully in the simpler setting of supersymmetric Wess-Zumino quantum mechanics. This model provides a perfect testing ground. It has both bosonic and fermionic degrees of freedom. It features a superpotential W, and it possesses two supersymmetries in the continuum. By learning to discretize Wess-Zumino QM correctly, defining derivatives, enforcing hermiticity, and eliminating fermion doublers while preserving one half of supersymmetry, we lay the groundwork for the full lattice BFSS model, where the same structure returns in a richer matrix-valued form. Let us begin with the simplest supersymmetric system, Wess-Zumino quantum mechanics. It is a one-dimensional supersymmetric field theory with two supercharges, often viewed as the dimensional reduction of the Wess-Zumino model in higher dimensions. The theory contains one real scalar field, phi of t, and one pair of Grassmann fermions, psi and psi bar. The dynamics are encoded in a single real function, W of phi, known as the superpotential, which determines both the scalar potential and the Yukawa coupling. The system is formulated in Euclidean time with periodic boundary conditions for the bosons and anti-periodic ones for the fermions. The total Euclidean time interval is beta, the inverse temperature, so this formulation naturally describes a finite temperature quantum system. The Euclidean continuum action is given in equation 1. This is the minimal supersymmetric system that exhibits both boson-fermion pairing and supersymmetry breaking at finite temperature. On the lattice, this model will serve as our prototype for understanding the fermion doubling problem and how to eliminate it while retaining supersymmetry. When discretized on a lattice of lambda sites with spacing A, the model becomes ultra-local. The lattice action, shown in equation 2, is a sum over sites of 1/2 phi k phi plus 1/2 w prime squared plus psi bar d psi. This is the starting point for exploring how to choose a lattice derivative that preserves hermiticity, avoids fermion doubling, and possibly retains part of supersymmetry. To analyze the lattice derivatives, we move to momentum space using the Fourier transform on the Euclidean time circle. The field f of t can be expanded in discrete Fourier modes with momenta p equals 2 pi k over beta, where beta equals the total Euclidean time, or inverse temperature, and k runs from 0 to lambda minus 1. On the lattice, time becomes discrete with spacing a, and the relation beta equals a times lambda holds. The discrete field values are f sub n, and the corresponding lattice momenta are p sub k equals 2 pi k over lambda. This allows us to replace derivatives by simple multiplicative factors in momentum space, a crucial step for analyzing the spectrum of lattice operators. The inner product between two lattice fields is defined as a simple sum over lattice sites, and the hermiticity condition d dagger equals minus d ensures that the fermionic term psi bar d psi remains real. Let us now define the basic lattice derivatives. The forward derivative, denoted partial r, acts as f at n plus 1 minus f at n over a. The backward derivative, partial L, acts as f at n minus f at n minus 1 over a. These two operators are related by Hermitian conjugation. The adjoint of partial L is minus partial r. The eigenvalues of the corresponding momentum operators are easily computed. They are given in equation 7. From these, we define two combinations. The symmetric derivative, partial s equals 1/2 times partial r minus partial L, and the antisymmetric derivative, partial a equals 1/2 times partial r plus partial L. The eigenvalues of the corresponding momentum operators are given in equation 9. The naive Dirac operator uses this antisymmetric derivative. D acting on f at site n equals 1 over 2a times f at n plus 1 minus f at n minus 1. The antisymmetric derivative connects sites separated by two lattice spacings instead of adjacent ones. This two-step stencil is the origin of the fermion doubling problem. In momentum space, the corresponding momentum operator, p sub a equals minus I times partial a, has eigenvalues proportional to sine pk. Because the sine function vanishes not only at p equals 0, but also at p equals pi, we obtain two linear low-energy branches, one with small momentum and the other one with high momentum. Around p equals 0, the eigenvalues are approximately lambda sub k equals 2 pi k over beta. Around p equals pi, or equivalently k near lambda over 2, they become lambda tilde sub k equals minus 2 pi tilde k over beta. These two regions both behave like light fermions in the continuum limit, producing two species instead of one. The extra mode at p equals pi corresponds to a spurious doubler, a state with high momentum but low energy. In the propagator, it manifests as a second pole, contaminating the physical spectrum. To correct the doubling problem, we first define the lattice Laplacian, which plays a central role in Wilson's solution. For normal lattice derivatives, we take partial equal partial r, partial dagger equal minus partial L, and they commute, so their commutator is 0. Under these conditions, the Laplacian is uniquely defined and Hermitian. It is given by delta equals partial L times partial r, which also equals partial r times partial L. Acting on any lattice field F, we get equation 14. We will now use this operator to build the Wilson term, which removes the unphysical doubler branch without altering the continuum physics. The key idea of the Wilson term is to add a small correction proportional to the Laplacian. The Laplacian itself is directly proportional to the symmetric derivative, partial s equals 1 over 2a times f at n plus 1 plus f at n minus 1 minus 2f at n, and delta equals 2 over a times partial s. The Wilson term is then written as partial w equals partial a minus ra over 2 times delta, which we can also express as partial w equals partial a minus r partial s. This is given in equation 16. This defines a one-parameter family of ultralocal lattice derivatives. Let us now examine how the Wilson term modifies the spectrum of the lattice momentum operator. The eigenvalues of the momentum operator, Pw equals minus I times partial W, are given in equation 17. For small momenta, where p sub k is near 0, the expansion gives lambda sub kw approximately 2 pi k over beta minus IRA over 2 times 2 pi k over beta squared. Near the Brillouin zone edge, where p sub k is close to pi, we write k equals lambda over 2 plus hat k, and find lambda hat kw approximately minus 2 pi hat k over beta minus 2 IR over a plus IRA over 2 times 2 pi hat k over beta squared. We see that the small momentum branch remains light, since the Wilson correction vanishes like a k squared, while the doubler branch is lifted by a large mass gap of order 1 over a. In other words, the physical fermions near p equals 0 stay in the spectrum, and the unphysical fermion near p equals pi is pushed to infinitely high energy in the continuum limit. This mechanism, simple yet elegant, is how the Wilson prescription eliminates fermion doubling on the lattice. The Stratonovich prescription provides a supersymmetric regularization of the Wess-Zumino model on the lattice. It satisfies three key properties. First, there is no fermion doubling because the prescription naturally includes a Wilson term. Second, there is no fine-tuning required in the continuum limit since the action preserves one supercharge on the lattice, and that is sufficient to recover full supersymmetry as the lattice spacing goes to 0. Third, the fermion determinant has the correct continuum limit, ensuring the right quantum measure. The idea is to start from the antisymmetric derivative, partial sub a, and then apply a shifted superpotential together with an improvement term. These two modifications, the shift and the improvement, effectively turn partial sub a into the backward derivative partial sub L, introducing a built-in Wilson term while still preserving 1/2 of supersymmetry. The resulting lattice action is given in equation 20. Here, sigma sub n equals the midpoint, the average of phi sub n and phi sub n minus 1. This formulation achieves a delicate balance. It eliminates doublers through the built-in Wilson term, and it keeps a remnant of supersymmetry exact at finite lattice spacing, guaranteeing the proper continuum restoration of the full theory.